In the last video, we took a look at solving y prime equals ay plus b, and I just wrote down what the solution was. Today, I'd like to, or in this video, I just wanted to say why this is the solution, and also maybe solve a couple of differential equations using this. Okay, so why is this the solution first? So if we start off with y prime equals ay plus b, then consider the differential equation y plus b over a prime, and let's see if we get the same thing, a times y plus b over a. Okay, so if you were to actually write this out, right, this is the derivative of y, which would be just y prime. So this side just becomes y prime. And then this side, if you multiplied it out, becomes ay plus b. So we have the original differential equation here. Now notice that this is something derivative equals a constant times something. And we already know how to solve that equation. That equation is solved as, let me get back to my other one. So the solution to this differential equation is c times e to the at. Good. So then just bring the b over a over, and therefore our y of t is equal to c e to the at minus b over a. Okay, so that's starting off with ay plus b. Right, so again, this pairing is what we're looking at. Good. So now, before we actually solve this, one question that we often ask is, what does y do as t gets very large? And so you can see that there's two cases depending on what a is. Right, because if a is negative, then e to the at goes to 0 as t goes to positive infinity. Right? And so, therefore, y would go to minus b over a. And in fact, this is kind of an interesting situation, because consider the case where c is equal to 0, so that y is equal to minus b over a. Then what is y prime? And y prime is equal to 0, and this is actually true for all time, right? Because our derivative doesn't depend on time. And so this solution doesn't change in time. This is called an equilibrium solution. So an equilibrium solution is a constant solution because it never changes in time to the differential equation. Not all differential equations have equilibrium, but some do. And this is, if a is less than, or actually doesn't matter what a is, this equation will always have an equilibrium solution at minus b over a. By the way, it is a special solution. Okay, so therefore, if I were to actually plot this in time, right, and if one of these, let's see, I guess we're saying a is negative, right? So minus b over a is actually above if b is positive. Okay, and then e to the at is going to 0, so all the other solutions are going to be going towards my equilibrium. And so this is what different solutions will look like. It depends on where they start, right? So this is this is the solution where c equals 0, c equals 0, and then for like c equals 1, excuse me, we might be here. And this might be c equals minus 1, and etc. Okay, so these are different c's, and so when you're looking at this general solution, let me write it with red here. This is the general solution. So how many solutions does the general solution represent? typically an infinite number, because there's always going to be some kind of parameter that needs to be determined. And where does that parameter come from? Well, that parameter comes from, in physics, you could think of it as an initial condition, initial position, but just in general, it's a point at which it's a point. I guess we could take the point at time 0. In that case, that would be there, or there, or there. Okay, so it's a point that the curve goes through. And so we think of the general solution as like a family of solutions. Good. Okay. So that is the general case. Let's look at a specific example now. Just a straightforward one. Example. Oops, I thought I changed my color there. Y prime equals y plus 2. And we want y of 0 to be equal to 2. Find y of t. Well, from our solution up here, we see a is equal to 1 and b is equal to 2. And so the solution is ce to the t minus 2. Now I want y of 0 to be equal to 2. And so that gives me the ability to solve for c. So if I put in 0, I get ce to the 0 minus 2. Whoops. My computer's telling me there's a Java update. Later. Minus 2 equals c minus 2. I want that to be equal to 2. So therefore my c is equal to 4. And so my specific solution here is going to be 4e to the t minus 2. Good. Now, just for some vocabulary, this again is the general solution, and this is our specific solution. And this was our initial condition. Okay, so we use the initial condition in order to go from a general solution to a specific solution. Good. Now I think you're ready for the homework. There was a couple of hints that I typically give. One of them is from 1.3, let's see, 1.3, number 14. And the hint is that we need to be able to differentiate the function f of t times the integral from 0 to t g of s ds. Do you remember how to do that? Well, you want to think of this as a product rule. And so the derivative will be f prime of t times our integral. Now remember, this is a function of t, right? Because the t is up here. Okay, so that is a function of t plus f of t. And now I need the derivative of this. Do we remember what that is? From FTC, Fundamental Theorem of Calculus, says that that is just g of t. Good, so this is the derivative of that expression. And that's what we needed to solve number 14. For number 25, in 1.3, I just wanted to make a note about the cosh function. Y equals the hyperbolic cosine of x. I know some of us haven't seen the hyperbolic sines and cosines before, and so there is some stuff, review sheet on the web. That's on our class website, class web page. That's not on Canvas. It's on the regular class website. What you can do is if you want to work with the hyperbolic cosine, go ahead and rewrite it. It can be written in terms of the exponential function. Okay, and so if y is equal to this, then we can write y prime pretty easily. And so this happens to be the hyperbolic sine. And so that's kind of interesting. The derivative of the hyperbolic cosine is the hyperbolic sine, and you can also see that the derivative of the hyperbolic sine is the hyperbolic cosine. So that's kind of fun. Hyperbolic sine and cosine are useful in different situations. So it's good to learn them, especially if you're going to be an engineer. Okay, I'm up to my time limit now. That's it. Have fun with the homework, and if you have any questions about anything, I will be around, so send me an email. Talk to you later.